Hello, everybody. I think this is our 33rd video lecture. And we missed the 32nd one in terms we had the class, but the equipment wasn't working. So I will redo the video material and post it probably tomorrow. In the meantime, I want to start today by reminding you we have the homework assignment that is due on Friday. So homework 5. It's due on Friday. Then we're going to have test 2. Will be on Wednesday. I think that's April 29th. We have received a study guide for the test 2, and I was thinking that maybe we had a study session for the exam, and I don't know when is a good day for us to have it. Is it better for us to have it on Tuesday, Monday night, and Tuesday night?
Whatever works for you guys.
Is that okay? Monday and Tuesday, we have 2 days? Okay, so probably in the afternoon, late evening, early evening, I should say. Maybe starting 5:30 or something like that to 7:30. We do both days. So that's what I'm thinking. So study sessions on Monday. That's not tonight, but a week from tonight. And Tuesday. Let's say from maybe 5:30 until 7:30 in this room. It's okay? Go ahead, Alan.
Do we know the day of the final is?
Yes. The day of the final is going to be the following Wednesday, so I think that's the 6th. Okay? And I believe it'll be from 12 till 2. I think it is in this room, but I'm not sure of that. But it is Wednesday. It should be listed on your syllabus, and I can look up when it is. And I will for next time.
Are we going to get another study guide for that, or is it going to be different?
I think that it's still a little undecided. Yes, you don't get a study guide. It's been decided. There it is. So I'll give you something to narrow down what I'll ask. Okay. Okay.
And is there going to be any material that we cover after the second exam material that is on the final but not on the second exam?
The answer is no, and well, I shouldn't say that. That's still undecided. Okay, I haven't decided, so I shouldn't have said that. So, truthfully, those algebraic properties of continuous functions, which what we did last time, is that on the study guide for test? Anybody have test 2 study guide? Is that on there? Let's take a second.
I don't believe it is on there.
Yeah. So we probably are covering material that isn't listed here already. Okay. And so I think the answer is yes. We will have some stuff on the final that's not going to be on test 2. Okay. So some stuff that we are covering now that's not on test 2. So I'll include that on the study guide. Okay. Is that okay with everybody? Okay. Well, what about questions from the homework? Does anybody have some problems? Like, can you do something like this, or can you give me a hint about this? Any questions anybody wants to ask? Classmates that are not here probably saying, "Ask something. Ask this." Anybody got anything in mind?
For number 3, you
Yes.
just want us to say whether it is or is not. Do you want any work shown? with
Nope.
That. Okay.
For number 3, it has to do with being cluster point or not, and so I just want you to say yes or no.
Can you do an example number 4?
Yes, ma'am, I sure can. So for number 4, it takes me a minute to make up a problem. So if you'll forgive me. Takes a minute, doesn't take that long. Here's an example. Suppose F goes from R to R, such that, let's say minus x minus 2 squared plus 3 is less than or equal to f of x, which is going to be less than or equal to, let's make this 2 times x minus 2 to be squared plus 3. Right. And someone says, find the limit as x goes to 2 of f of x. So here's what I'm going to tell you. I forgot, who asked me this? Was it you, Melissa, that asked me this type of problem? Okay, so Melissa, the question has to do with the limit of the function. We don't know what the function is defined to be. So in our definition of limit, we have an epsilon delta, but we need to know what f of x is really to work with that definition. So instead, what this resembles is something that maybe possibly we could use the squeeze theorem on. And so that's what I've got in mind. Here, we will use the squeeze theorem. So what does the squeeze theorem say? It says, hey, look, when you're looking at a function in the middle, and it's sandwiched in between a lower function and a bigger function for all x values except maybe, in their common domain, except maybe at c, the point of interest. Then if you take the limit of the smaller function and the limit of the bigger function at x equal to c, which in this case is 2, and you get the same answer, it's going to force the middle function's limit to also be the same number. Is that okay? So I made up this problem. Let's see. Note the limit as x goes to 2 of minus the quantity x minus 2 to be squared plus 3. Now, for this problem, Melissa and everybody else in the room, I believe I've said this to you, that if you're looking at a polynomial function and taking its limit, then the answer is the polynomial evaluated at c, where you're taking the limit. Okay? I believe I've said that to you. Did you guys hear me? Okay? So that's something that's been covered. So here, what I'm telling you is you just stick in 2. You stick in 2 for x. 2 minus 2 is 0. 0 squared is 0. Minus 0 is minus 0. This equals to 3. And if you take the limit of the bigger function, as x goes to 2, 2 times x minus 2 squared plus 3. Here, I stick in 2 because this is a polynomial function, so I just stick in 2. To get this limit, I just evaluate this polynomial with 2. 2 minus 2 is 0, squared is 0, 0 times 2 is 0, 0 plus 3 is 3. So by the squeeze theorem, by the squeeze theorem, the limit as x goes to 2 of the middle function also has to be 3. And that's, Melissa, what I have in mind for part. Well, for problem 4. I'm done with this example. Is that okay? would anybody like to ask about the homework? Any other questions? Okay. Well, then I'll move on. So here's where we are. So I had mentioned this, that in the last lecture, which we did not get videotaped, we proved, so last time, which I will videotape and put up, not just yet. We proved that if F and G are continuous, then 1 F plus G is continuous, either on FC or on a set, common set. 2 F minus G is continuous. 3 F times G is continuous. And fourthly, if G of X is different from 0 on its domain, and this is stronger than we need, then F divided by G is continuous on its domain. It's okay with everybody? So that's what we've shown. And then we also showed something else. So this fact we really broke up into two ways. We did it for a point, C, and we also did it for a set. Okay, or at least stated it for a set. We also had the following fact that we proved. If, so this is a fact. It's recall, we did this. If F is continuous at C, then the absolute value of F, about B of X, which is defined to be F of X inside absolute values, is continuous to C. And that proof used the epsilon delta definition of continuity, but it also used a fact about relating absolute values of quantities. Well, this fact is something we did, and it's about continuity of the absolute value of F at a point C. And we have an analysis statement kind of extending this. So here's new, I'm reading. If F goes from A to R, and F is, and B is a subset of A, with F being continuous on B. And what we mean by being continuous on B, if you remember, it means that F is continuous for every C in B. Then the absolute value of F is continuous on B. Let's do a proof of that. It's very simple. Okay, so the proof will let F go from A into R be continuous? At C, be continuous at or on B, you're right, John, thank you, which is a subset of A. We want to show absolute value of F is continuous on B. So what does it mean to show a function, in this case it's the absolute value of F, is continuous on a set? It means you have to show that this function is continuous for every point in this set. So I'll just let little c be an element of B. We want to show this arbitrary point in B, and so we want to show the absolute value of F is continuous to C. Well, how do I do that? Well, note, since F is continuous on B, then the function F is continuous with C. And the previous fact that I had stated and proven last time implies the absolute value of F is continuous at C. Thus, since the absolute value of F is continuous at an arbitrary point in D, the absolute value of F is continuous on D. And that is the proof.
Is that going to be the only question on our final? Is that proof?
No, sir.
That's a shame.
There will be other questions, ones that you can do if you study that.
I'm just trying to get points where I can.
Well, it might be there. It's good to know.
You won't remember it. Thanks, Brad.
Well, I want to do a fact that's similar, talk about something besides absolute value. So here, let's say as a theorem or a fact, and let me write this down appropriately by writing down exactly what's in the book here. So here's the way that it's said. It says, let A be a subset of R, F go from A to R, such that, or with, F of X is greater than or equal to 0 for all X element of A. All right. Define the square root of F as a function that goes from A into R by the square root of F acting on X is equal to the square root of F of X, which we could take because F of X is a non-negative number. So we have two parts. A, if F is continuous at C that's in A, then the square root of F is continuous at C. Part B. So the first statement for A was about continuity at a point. And we're going to extend that for fact B by continuity on a set. That's exactly right. And this is what they say here. If F is continuous on, in this case they say A, just on the whole set, then the square root of F is continuous on A. Okay, we want to prove this. Really, proving A is what's going to lead to the proof of B. Once you have A, you have B. Okay. So let's look at this proof. So we're going to let F go from A to R with F of X be greater than or equal to 0 for all X. For part A, we let F, well, I should say here, we let C be an element of A with such that F is continuous at C. We want to show the square root of F is continuous at C. Well, I didn't give this enough thought before I came in here. But the way I'm going to do it is different than what I said. So here's what I want to do. We will prove this. One, showing that f of x, I'm sorry, I'm going to call it g of x. G of x equal to the square root of x is continuous at c greater than or equal to 0. I'm going to show this. And 2, I'll put this in parentheses, the composition of continuous functions is continuous. So there's two things I want to show. Okay. So I've broken the problem down into 2 parts. I'm going to show that g of x equal to the square root of x is a continuous function. Okay, so here's this. I'm going to call this lemma. This is a statement that we need to prove something else. Okay, so let let g of x go from 0 to infinity into R be defined by g of x is equal to the square root of x. Let C be greater than or equal to 0, so something here. We will show then G is continuous at C. Okay. I'm going to do this through the definition of continuity. Okay, so here's what I'm going to do. We're going to let epsilon greater than 0 be given. What do I need? We need a right greater than 0, such that for all x element of 0 to infinity with x minus c being less than delta, then the absolute value of g of x in this case, which is the square root of x, minus g of c. What's that? Square root of c. That's correct. Will be less than epsilon. So that's what I want to have happen. Okay. So we want the square root of x minus the square root of c to be less than delta. That's what I want. Less than epsilon. That's what I want. And I'm hopeful I can get some control over that distance by being able to control the absolute value of x minus c. Okay? So I know I moved the camera. Remember, when I get to control this, I get to control the absolute value of x minus c. I can make it less than any number I want. Okay? Any possible. Well, here's what I'll say. Note, in trying to figure this out, the absolute value of x minus c, it really does have the absolute value of the square root of x minus the square root of c involved in it. And then I can think of this as the difference between two squares, okay? And so here, we can say this is really equal to the absolute value of the square root of x minus the square root of c plus, or not plus, but times, yeah, write down something correct now. The square root of x plus the square root of c. And that's equal to the absolute value of x minus the square root of c, okay, times the square root of x plus c. Square root of x plus square root of c. Now I'm going to talk about this part for a second. Square root of x, I'll stop for a second. Anybody have any questions?
That should be square root of x on that first part again, right?
Sure should. Thank you very much. All right. Now this is the guy I get to control. And by controlling it, I'm hoping I control this part, okay? By controlling all of this. Well, I want to say this is going to be less than, let's make sure I'm doing this right. This is going to be less than, this part right here is always this part right here is always bigger than or equal to the square root of c. First of all, the square root of x is a non-negative number. You take the square root of it, you get something that's bigger than or equal to 0. And the square root of c, and c is a non-negative number, so its square root is bigger than or equal to 0. So if you add in two non-negative things, you get something non-negative. When you take its absolute value, it's itself. This is non-negative, so when you add it to c, it got bigger than, when you add it to the square root of c, it got bigger than the square root of c. So this says this is less than the square root of x minus the square root of c times the square root of c. Is that okay? No, this would be the other way. This part. Is that okay? Good. That's what I need. That's what I need. I need this. I do need this. So this is something to note. Is that okay? Now I can make this part right here be less than anything I want. Okay? Be less than whatever I want to put here. I know it's being written kind of in the opposite direction of what we're used to. We have this being less than whatever we want. I would make it less than. And whatever I make it less than, I want it to force this part to be less than epsilon. Is that okay? Okay. So I want this to be less than epsilon.
Cases?
No, not necessarily. I think we should think of, well, maybe we are because of the square root of c.
It could be 0.
Yeah, it could be 0. So let's think of it this way. So so case 1, that's right. If c is non-zero, then we let delta be equal to. All right. So I want to get some explaining. Look, I can put whatever I want here. Whatever I put, it's going to be bigger than this, okay? And what I want to have is something here that when I solve for the absolute value of the square root of x minus the square root of c, I'm left with epsilon. So what should I put here? I should put epsilon times the square root of c.
I think it should be divided by.
Now let's put square root, let's put epsilon times the square root of c. Okay. Okay. Then for all x greater than or equal to 0, because that's the x that we're talking about that's in the domain, with absolute value of x minus c is less than delta, we have the absolute value of x minus c being less than epsilon times the square root of c. So that's my delta. This implies, I'll tell you something smaller than the absolute value of x minus c. Okay, something smaller right here. Thus, for all x greater than or equal to 0, we have, what's smaller than this? What's smaller than this is the absolute value of the square root of x minus the square root of c times, well, the absolute value of the square root of c. But what's the absolute value of the square root of c? It's the square root of c. That part is really just the square root of c. And that's going to be less than epsilon over c. So here's what I'm doing. Megan, this is, right where I'm pointing, is something we have. Okay, this line. And all I'm doing, Melissa, is replacing the absolute value of x minus c by something smaller. How do I know that this is smaller? Because that's what I did right here, this way. Okay. So the smaller guy has to be less than epsilon times square root of c. And then to solve for all x greater than or equal to 0, we have, if I solve for just this part, we have the square root of x minus the square root of c would be less than less than what?
Epsilon.
Epsilon. And that's what I wanted. So there it is. Okay? That's in this case. Taste it. If C is equal to zero. Okay, so I need to think about this just for a second. Then we want a delta greater than 0 such that for all x greater than or equal to 0 with the absolute value of x minus c, that's 0, is less than delta, then that will force the square root of x minus the square root of 0, that's c in this case, to be less than epsilon. So we want, well, here I said square root of c, but that's really square root of 0. We want the square root of x inside absolute values to be less than epsilon. Well, the square root of x is a positive, is a non-negative number. Its absolute value is non-negative. So we want the square root of x to be less than epsilon, where both of these guys are positive. So if I square both sides, that's the same thing as wanting. We want x to be less than what?
Epsilon squared.
Now remember, x is positive. So that means we want the absolute value of x to be less than epsilon squared. That means we want x minus 0 to, x minus 0 inside absolute value to be less than epsilon squared. So I hope it's pretty clear. This is the guy I get to control. I get to make it less than any delta I want. But if I make it less than a particular delta, it's going to give me what I want. What delta? What should you let delta be? What is it? Delta equal. Let delta equal
Epsilon squared.
Yeah. And so that works for this case. So in all possible cases, there exists a delta such that for all x greater than or equal to 0, with x minus c being less than delta, then that forces the square root of x minus the square root of c to be less than epsilon. Thus, the square root of x is continuous at c. At c that's greater than or equal to 0. What that says, so g of x equal to the square root of x. If it's continuous at any point that's greater than or equal to 0, then it's continuous on the set zero to infinity, which is really its domain. Call it that. So I've shown that the square root of x is continuous. Remember what I'm trying to show is the square root of f is continuous if f is continuous. Yeah? Okay, I said I would do it in two ways, two things. This was the first thing. I proved the first thing. Second thing we need to prove is this one. Sorry. So this ends proof of lemma. Number two, here's a lemma. It's a theorem in the book. I'm writing down lemma because I'm using it. It says, let A and B be subsets of R. And F go from A to R, and G go from B to R. B functions such that f of A is contained in B. So F grabs things, it sends them to things, and what it sends them to are in the domain of G. John, do you have a question?
I don't know, I'm just thinking about something.
All right, I'm going to keep writing. What do you think? If F is continuous, at some point C in A, and G is continuous. At B equal to F of C, that's an element of big B, then the composition G of F, which acts from A to R, defined by G of F, the composition of X is equal to G evaluated, whatever F of X is continuous at C.
Okay.
Yes, sir.
Would it be, is that the, is what we have written here the same thing as saying that F goes, or is that the same thing as saying that F goes from A to B?
Yes. F grabs things in A and sends them to things that are in B.
Okay. That's all I have.
Yes, sir. All right, proof. So here we're going to let F go from A to R, F of A be contained in B, F be continuous at C, that's an element of A. We're going to let G go from B to R with G being continuous. At C. I'm sorry, at B equal to F of C. We want to show to show that g of f as a function is continuous at C. All right, so how do we do this? Well, here's what we do. We're going to do this by the definition. We're going to be let f something greater than 0 be given. We need to show, or we need a, what do I need? I'm trying to show continuity. Yeah, I need a delta greater than 0, such that for all x, now look, it's in the domain of g of f, which is a, with x minus c being less than delta, then absolute value of g of f of x minus g of f of c, that's right, Dalton, will be less than epsilon. So we want absolute value of g evaluated at f of x minus g evaluated at f of c, which is really the b, to be less than epsilon. So we can think of these as output values of g. Is that okay? Well, what do I know? Since g is continuous at, well, it was continuous at b, which was the same thing as f of, okay, a little bit better, f of c, the point, okay? It's continuous at b equal to f of c. So g is continuous at this point. This is just a number, okay? F of c is just a number. G is continuous. And I've been given an epsilon. So there exists, let's call it for a second delta 1. There exists a delta 1 greater than 0, such that for all, now wait a minute, we're talking about g, okay? We're talking about g. Where is g living? Where does it work? It works on what set? B. B, such that for all, I'm going to say y elements of B with
absolute value y minus b.
Y minus, right, I'm going to call it f of c, or y minus b, doesn't matter, one of the two. We're going to finish this. All right, I'm getting excited. With the absolute value of y minus f of c, that's what I'm writing, so it's b, is less than delta of 1, then that forces the output values of g of y, that's a y, minus g of f of c to be, inside absolute values, to be less than epsilon. Okay? So, hey, look, as long as the guys in the set B, big B, are close enough to f of c, their output values that g is going to work with, g is going to yield out, are going to be close to g of f of c in epsilon units. Okay? That's what I'm saying. One more minute. So I want to make sure that the y values I'm looking at in B are close enough to
F of C.
F of C. Well, how can I do that? I do that through the fact that F is continuous at C. One more second. Since there exists a delta greater than 0, such that for F's continuity, delta 1 is acting like the role of epsilon for the definition for F being continuous. Okay? So such that there exists a delta greater than 0, such that for all x element of A, with, I'm almost done, with x minus c being less than delta, then, this was a 1, delta's a 1, then the output values, so that's f of x minus f of c, will be less than delta sub 1. So, for all x element of A with, this is the last line, x minus c being less than delta, it's the next last line. All right, this happens, and then g of these things would happen. This would happen, will be less than delta, but delta sub 1, but these are input values for g. And if the input values for g are within delta 1 units of f of c, then the output values of g acting on these will be within epsilon units of g of c. It's because this is happening, this happens. And so g of f is continuous. I'm done. At c. Okay, so that's the two lemmas that we will use to prove that the square root of a continuous function is going to be continuous. So we still need to do that. Thank you very much for your time and patience.